Welcome everyone. My name is Kevin Oshiro and I'm a member of the Application Engineering Group at MathWorks. The objective of this presentation is to provide you with an overview of how to conduct an HEV design optimization study. I will go over 3 topics in this example. First, I'll cover an introduction to optimization and MathWorks optimization tools. Then I'll go over simultaneously optimizing control and component parameters. And finally, I'll go over an example of finding a common set of control parameters for various driving conditions. Let's start this discussion with an introduction to optimization. Optimization is a field of mathematics, and MathWorks provides several tools to solve optimization problems. HEV development is all about optimizing your designs. The focus of this presentation is on the optimization methodology in order to solve problems on your own. So what is optimization? Optimization is minimizing or maximizing objective functions subject to a set of constraints. The objective function is what you're trying to achieve, and it can be linear or nonlinear. For example, you can try to minimize a measured signal in your Simulink model. Design variables are the parameters that need to be adjusted. The design variables can be discrete or integers. An example of design variables are physical model parameters or controller gains. And constraints are the bounds of the design variables. They can be linear or nonlinear. Example of constraints are minimum or maximum values of actuator speed or torques. MathWorks has several optimization tools. The first is the optimization toolbox in MATLAB. It solves linear, quadratic, integer, and nonlinear optimization problems. The next product is the global optimization toolbox in MATLAB. It provides functions that search for global solutions to problems that contain multiple minima or maxima, as shown in the figure. And there is the Simulink Design Optimization, also known as SDO. A very nice feature of SDO is that it utilizes a user interface, making it a good engineering design tool. And it uses functions from the optimization and global optimization toolboxes. I will show how to use SDO in the following examples. I will now demonstrate 2 HEV design optimization examples. The first example will show how to simultaneously optimize control and component parameters. And the second example will show how to find a common set of control parameters for various driving conditions. Let's start with the first example. This example is based on a multi-mode HEV from the following SAE paper titled Development of a New Two-Motor Plug-in Hybrid System by Higuchi and co-authors. This is the HEV system in the model year 2014 and later Honda Accord hybrids. It has 3 modes of operation. The first is EV mode, where the vehicle is powered by only the battery and motor. It also has a series hybrid mode, where the engine is the prime mover for a generator, which produces more electrical power, but the wheels are still only driven by the main traction motor. And it has an engine mode, where the mechanical clutch is closed and the engine is coupled to the wheels. The motor is always connected to the wheels, so it can also provide power as well. The HEV supervisory control and operating modes are shown in the rule-based figure on the right. At low speeds and power, EV mode is used. At higher speeds and higher powers, series mode is used. And at lower power and higher speeds, like at highway speed cruising, the engine mode is used. The design optimization problem setup consists of the following. We want to maximize the MPG equivalent over 2 drive cycles, FTP 75 and highway FET. We will also use a weighting function to optimize the 2 drive cycles as shown. The rule-based mode boundaries are made into 5 design variables as shown in the figure. A component hardware parameter, the differential ratio, was also added so that it can be simultaneously optimized along with the control parameters. To conduct this optimization study, Simulink Design Optimization was used. It was done on a standard laptop with 2 cores, and the MathWorks Parallel Computing Toolbox was used to utilize both cores. To open Simulink Design Optimization, go to the Analysis menu and select Response Optimization. A response optimization user interface will open. The first step is to add the design variables, which are the variables which Simulink Design Optimization will vary during the optimization process. This is where you specify the 5 control parameters and the 1 component parameter. It is very important to set the minimum and maximum ranges for all the design variables. Set them to realistic values or the actual physical limits in order to minimize the design space of the optimizer. The next step is to enter the uncertain variables. Uncertain variables are typically used to help you optimize for robustness. For example, you can put in a range of uncertain values and SDO will optimize over that range. We will use uncertain variables in a more creative way and use it as integers to specify the drive cycle used. The drive cycle parameter gets used several ways. First, as an index to the stop time vector. This was done because the FTP75 cycle is much longer than the highway FET cycle. When simulating, you want the stop time to change depending on which cycle is selected. The input to a multi-port switch, which selects the weighting factor for the miles per gallon equivalent signal, also depends on the cycle used. And not shown is that the drive cycle parameter is also used to select the multi-port switch for the drive cycle selector block. Next, we will set up the cost function. In this case, we will select the weighted miles per gallon equivalent signal in the model, and we want to maximize its final value. So we go to Select New, Signal Property, and set up the options as shown. Then you can select the weighted miles per gallon equivalent signal directly in the model. Now we select the Options icon and go to the Optimization Options tab. We will use Pattern Search, which is a global optimization direct search method. We will use the positive basis 2n search method, which is the default polling method, and start with the tolerances and settings shown. If the optimization doesn't improve much, you can tighten these tolerances. Here are some best practices for speeding up the optimization run. Use accelerator mode and fast restart. Accelerator mode generates an execution engine in memory for the top level model only. And fast restart avoids compiling the model again. So this is good for simulating models iteratively to tune parameters. Also use the parallel computing toolbox. This enables the parallel pool, meaning it'll utilize the multiple cores of your machine. And specify a simulation timeout. This is the time to wait before stopping a simulation. With the setup complete, you can save your session, so you don't have to redo all those button clicks again. You can then press Optimize. The optimization time will depend on the complexity of your model, optimization setup, and number of cores on your computer. For a 2-core laptop, this optimization problem takes about 12 hours. Note the design variables are changing over different iterations. This is what you want to see, that the optimization is actually trying out different combinations of design variables. Note that the signal property is trending up. We are maximizing miles per gallon equivalent, so this is what you want to see as well. Here is a summary of results. We wanted to simultaneously optimize 5 control parameters and 1 component parameter over 2 different drive cycles. We used the powertrain block set multi-mode HEV model, Simulink Design Optimization, and the 2-core laptop. The optimization process took about 12 hours. The optimization produced new control parameters, which shifted the mode boundaries as shown, and a new differential ratio. This resulted in an improved miles per gallon equivalent over the 2 drive cycles. Now that you have seen the process for setting up an optimization problem using Simulink Design Optimization, you can conduct your own studies. How would you expand the example shown? Some suggestions are, you could try different initial battery state of charge points. This exercises the supervisory controller. You can add an objective to minimize the 0 to 60 mile per hour time. You could study component sizing. For example, you can optimize the battery capacity or cell configuration because this affects the vehicle's mass. You can try drive cycles, which include road grade. And these ideas can be carried out in Simulink Design Optimization using uncertain variables. Let's now go over the second example of finding a common set of control parameters for various driving conditions. If you watched the previous presentation on developing HEV control algorithms, we looked at a rule-based energy management strategy for a P2 hybrid electric vehicle. That algorithm was based on the work outlined in this white paper shown. It has 3 design parameters that we will look at to see if we can improve miles per gallon equivalent and minimize delta SOC over drive cycles in order to charge sustain. We want to find a common set of variables that works over various drive cycles. The cycles we will look at are FTP72 for city driving, highway FET, that represents highway cruising, and US06, which represents more aggressive driving. For review, parameter K1 is the power threshold between EV and parallel HEV modes. Parameter K2 will help dictate the power split between the engine and the motor while in parallel hybrid mode. And adjusting the ETA term was found to help charge sustain or minimize the delta SOC over a drive cycle. This is important because this P2 example did not have plug-in capability. For this example, I want to highlight how to use another feature of Simulink design optimization, which is called sensitivity analysis. Sensitivity analysis helps identify the parameters in the model that have the greatest impact on a cost function or a design requirement. So we can use it to determine how much the 3 control parameters affect fuel economy and ability to charge sustain. Sensitivity analysis has a user interface where you can create sample sets, define constraints, run Monte Carlo simulations, and speed up the process using parallel computing. Let's walk through the major steps for setting up a sensitivity analysis so that you can learn how to do it on your own. To open Simulink Design Optimization, go to the Analysis menu and select Sensitivity Analysis. The Sensitivity Analysis user interface will open. First, we need to select the design parameters. So we're going to select the 3 control parameters we are interested in, being the charge sustaining factor, also known as ETA, the minimum engine power, also known as K1, and the SOC charge factor, also known as K2. Then select OK. The next step is to generate random distributions of the 3 control parameters so that we can create a sample set describing the control parameter variations. So go to Generate Values and Generate Random Values. Set the number of samples, use at least 10 times the number of design variables. In this case, it was 30. The solvable sampling method is used because it is good at space filling. And the parameter distributions are set to uniform, but you can use other distributions if you know what they are. And enter the lower and upper values for each parameter as shown. This helps constrain the design space. You may have to experiment with these values if they are control values and you don't know what the appropriate ranges are. And then select OK. Now select the Plots tab, highlight the parameter set, and select the scatter plot. The diagonal plots show a histogram of the generated parameter values, and the off diagonal shows the pairwise plots of parameters. The idea here is now we have a design space of possible control parameter combinations. Now click on the Sensitivity Analysis tab and select New Requirement, Signal Property. Select the property to signal final value and set the type to maximize the property. We're going to select the MPGE signal and want to maximize this property. And select the plus push button. You will now have to navigate to the model, and you will go into the Visualization subsystem and select the US Fuel Economy MPGE signal. Go back to the user interface and select the MPGE signal as shown and hit the arrow button. Then select OK. We have to repeat this signal selection process for one more signal to create a constraint. This time it is for ensuring the final battery SOC does not drop more than 1% from the initial SOC. So we have to select New Requirement and Signal Property again. Select the property to signal final value. And set the type to constrain the property to be greater than or equal the bound. We're going to select the battery SOC signal and want to make sure the final SOC is greater than 59%, because the initial SOC is 60%. Then select the plus button. We now have to navigate back to the model and go back into the visualization subsystem, and this time select the battery SOC signal. And go back to the UI and select the battery SOC signal as shown and hit the arrow button. And select OK, and you can now close this requirement window. Now, an optional step is to right-click on each of the requirements and rename them for a better description as shown. Now, here are some best practices for speeding up the optimization run. Again, use accelerator mode and fast restart mode, like you did on the previous example. Use the parallel computing toolbox. Again, this enables the parallel pool and utilizes your multiple cores, and this is found under the options icon. To save this session so you don't have to redo any steps, select Store Intermediate Data and save the session. I typically denote this as a start or load session. Then you can press Evaluate Model. Now the sensitivity analysis tool will run the simulation over the 30 combinations of the 3 control parameters and see which one has the greatest impact on maximizing miles per gallon equivalent and charge sustaining. After the sensitivity analysis is complete, you can view the scatter plot results. Note that when maximizing a signal like we did with the MPGE, the results will end up with a negative sign. The scatter plots show the cost function value as a function of each parameter, the cost functions being the miles per gallon equivalent and the state of charge greater than 59%. You can right-click on the scatter plots for more options, such as overlaying a linear fit line. And if you go to the Statistics tab, you can compute statistics to generate a tornado plot, as shown at the bottom. You can rerun this analysis for each drive cycle. Set the drive cycle parameter accordingly in the base workspace to select between the cycles. But note the different results for each cycle. So for the highway FET, the charge sustaining factor had the highest correlation for charge sustaining, but the minimum engine power had the highest correlation for maximizing your MPGE. And for USO6, the charge sustaining factor had the highest correlation for both charge sustaining and maximizing your MPGE. And for your FTP 72 cycle, the minimum engine power had the highest correlation for maximizing MPGE and charge sustaining. So it appears that each control parameter has a different effect on maximizing MPGE or charge sustaining over different drive cycles. This may mean that it could be hard to tune this role-based controller to handle various driving conditions. So I took the parameters that produce the maximum MPGE and minimum delta SOC for each drive cycle, inserted them into the controller, and simulated over each drive cycle. And these are the results that were produced. Note the variation in the 3 control parameters. So the next step is to use the response optimization tool to attempt to find a unified set of parameters to maximize miles per gallon equivalent and minimize delta SOC over all 3 cycles. So like the first example, we can perform a response optimization to find the optimal design parameters over different drive cycles. We will again use the drive cycle variable as an uncertain variable to run all 3 cycles over one optimization iteration. And again, parallel computing is used to speed up the process. Because I went through the detailed steps of the setting up the response optimization in the first example, we will skip them here. I used the 3 control parameters as the design variables and maximized the miles per gallon equivalent signal and put constraints on the final SOC to be greater than 59% and less than 61% to make the delta SOC to be within plus or minus 1% from the initial SOC, which was 60%. And for your information, this optimization process took about 2.5 hours on a 6-core workstation machine. Here are the results of using response optimization. It found a single set of design variables that maximize the miles per gallon equivalent and also charge sustained. This is a very good result because the common set of parameters produced results that met or exceeded what was found in the initial sensitivity analysis study. These parameters should help ensure our role-based controller will work robustly over different driving conditions. This concludes the introduction to conducting HEV design optimization studies. We covered an overview of optimization and went through 2 examples showing how to simultaneously optimize control and component parameters and finding a common set of control parameters for various driving conditions. The important takeaway is that you can create your own optimization studies and use Simulink design optimization to solve them. This is also the last presentation on Introduction to Hybrid Electric Vehicle Modeling and Simulation. Hopefully you were able to view the previous presentations on HEV modeling and developing and implementing HEV control algorithms. Thank you again for watching.